Okay, so yesterday I had defined this problem called closest pair of points, and today we are going to look at an algorithm for that. So I'll just quickly repeat what I had said yesterday, that brute force will take order n square time, and we want an order n log n time algorithm, and we have this convention that the points are given in the form like p1 to pn, and the coordinates of a point pi is xi comma yi, and for pi comma pj, d of pi pj denotes Euclidean distance between pi and pj, and the goal is to find pi pj I not equal to j such that distance of pi pj is minimized. So that is the problem that we are going to solve. Okay, and we are going to assume that all x and y coordinates are different, and this can be done by rotating, applying a linear transform, which basically just rotates the points very slightly. Good. So we'll not worry about this assumption today. We'll just, how to get rid of it. But this is an assumption that we'll be using, that all the x and y coordinates of the points are different. Let's say. Okay. So now so we want to solve this problem. Given a set of endpoints, we want to find the closest pair. So before we get into the two-dimensional case, let's look at one dimension. Given endpoints on a line, or just on x-axis or whatever, find the closest pair. How can we do that? I mean, what is the again, a brute force, you take every pair and find their distance, that will take n square time. How can we do faster?
We sort the coordinates and then just take the distance between consecutive points.
Yeah. Sort coordinates, take distance between consecutive. Why? Because the closest points have to be consecutive in one dimension, right? So suppose we want to do something similar now, because okay, we don't want to spend the n square time, and now in two dimensions we want to do something similar. Let's say. So suppose we sorted points according to x coordinate. And then is this true that closest points are consecutive in this sorting?
No.
No, right? Because 2 points can be very close to each other and can be very far, because so again, and then you can have something like this, and then so this pair can be the closest, which is not consecutive in the sorting, right? So because you are just mapping them on x-axis. Right? Because the distance over the y-axis might matter. But still we want to do something similar, that if we can't get to consecutive, we want to do something similar, that we want to arrive at some similar notion in two dimension also, and we'll see how we can use that or arrive at that. Okay, but before that, let's again, so we want order n log n algorithm, right? So what do we want to do again? Divide the problem into two parts. Solve them recursively. and combine the solutions in order and time. Right. Again, so the basic same paradigm that we have or we had in the last lecture, we are trying to or will try to use the same. Okay. But now for dividing the points into two parts, it is going to be beneficial to have these points sorted in like, X and Y both. So for any subset, let's say, so at any stage of the recursion or at any stage of the algorithm, while recursing on set P prime, let's say, subset of P, we will have two sorted lists, P prime X and P prime Y. What is P prime X? Points in P prime sorted by ascending order of X coordinate. And P prime Y is again points in P prime sorted by ascending order of Y coordinate. So this is something we'll need, but for this you don't need to work again and again. Once you sort all the points, then you have got the thing. So we'll set up the recursion by sorting points in P by X coordinate and Y coordinate. And Y coordinate. And call those orderings Px and Py, as we have said. And this takes how much time? Order and log n, right? Because we are just sorting according to. And what we'll also do that in the Px thing, we'll also store the. So this is an array, right? This is an array of points are sorted according. But we also store the position the point is in Py. Okay, so that you can quickly just look through if you want to relative ordering in Py also of 2 points. If like given 2 points, you can just look at these. Okay. So good. So this is the thing that we are given n points 1 to n. Now we have sorted them according to their x coordinates and y coordinates. And now, like, that is just the initial setup from where we are going to start. Okay, so now let's look at the algorithmic part. I mean, this is also part of the algorithm, but this is just to set up the recursion. This is not going to be the recursive algorithm. Now, what does the recursive algorithm do? So, the recursive algorithm now looks at Px. So, looks at all the points. Okay. And suppose looks at Px. Suppose these are the points. And looks at sort of the middle point according to x coordinate. Okay, so suppose here there was a point. So look at, so let m is equal to n over 2 and look at x coordinate of mth entry in Px, right? And let that x coordinate be x star, right? So okay, suppose here is the axis. So you have this x star here. So this is the point which basically, this is the line basically which divides the plane in two halves such that equal number of points, roughly equal number of points are on each side. Okay. Good. So now let's make this list to be, now let's call this half as Q, this half as R. So let the set of points in the left half include this point if you want. So this mth entry or left half. So basically first m entries of px. B, Q, and the right half B, R. Okay. Now, whenever we have such Q and R, we also have this QX sorted points in Q according to X coordinate. And this you can get from PX like directly, right? And then you have QY, which is sorted lists of points in Q. And this is for, like, to construct this QY is why you had stored this, the pointer to the position in PY. Why? Because now you want to find this QY list that you want to sort the points in Q according to their Y coordinate, right? So how will you do that? Now you are going through Y coordinates of points in PQ. You don't know whether they are in Q or they are in R, whether you should put them in QY or not. So that's where, so you have this array, which is PY. You go to a point and see, okay, fine. Now where is it X thing? What is the index of this point in PX? And if that index is more than M, then you put it in R or don't put in Q. And if that index is less than or equal to M, then you put in Q. We are constructing QY, right? Then put in QY. Okay, so the point of storing this information, the index of the same point in the other list, is so that you can construct these lists QX and QY given PX and PY. Because this Q is defined not on, like, this Q is defined only on the basis of X coordinates. So Q and R are defined on the basis of X coordinates, but still you will need the orderings QX and QY to apply the recursion. Why? Because here we have the ordering PX and PY. So the algorithm will always assume that whatever set of points it is given with, it is going to be sorted according to X coordinates and Y coordinates. There are two lists given. Sorry. Any questions in this? Well, I take a sip of water. Any questions? What we have done till now? So we have basically divided the points into two halves, and we have just sorted them according to x and y coordinates. And how we have sorted? We have taken the help of the initial sorting that we had done of P according to x and y coordinates. Okay, good. So this is still the setting up part. Now suppose in the recursion, the closest points in Q and R. Okay. So let's say that in Q, the closest points of are Q0 star and Q1 star. And in R, they are R0 star and R1 star. I don't know why it's there. Okay, fine. Okay. So suppose the recursion has returned this. So what do we do? What do we want to do? We want to call the recursive procedure on these two sets of points. So the procedure returns with this that, okay, these are the 2 points which are closest on this side. These are the 2 points which are closest on this side. Let's say this is Q1 star, Q0 star. This is Q1 star. This is R0 star. This is R1 star. Okay, so the recursion comes with this. So now to combine, what do we have to find? What will we do that can combine now? Or what is it that we want to achieve? What kind of things that we want to find to combine these two solutions?
We have to check whether there exists a point in Q and another point in R such that the distance between those points is less than what we found up until now.
Exactly. So as Mani says, so let the minimum of distance of Q0, Q1, comma, distance of Q0 star, Q1 star, distance of R0 star, R1 star. Let this be delta. So delta is equal to, let's define delta to be this. Okay. So now we want to find if there exists some Q belonging to Q and R belonging to R such that D of Q comma R is less than delta. Right? So this is we want to figure out. This is what we want to figure out. Okay. And this doesn't again seem like a very trivial thing to do because again there are n over 2 points here, there are n over 2 points here, and in total you can again arbitrarily you have to like n square by 4 time it will take. I mean whatever order n square time. So whatever n square by 4 times some constant is equal to order n square time to figure out the distance between every pair. Okay. So that is something we want to avoid. We definitely don't want to do something like that. Okay. But let's look at now something else. So we have this delta, right? So we had this x star. This x star was the last x coordinate of anything in Q, right? So we have this x star. So again, so suppose this is the axis. So we have this x star. So this is x is equal to x star line, and let's call this line to be L. Okay. So where can these points lie? So here, this side is Q. So this side is Q. This side is R. Now, if there exists some q comma r such that q belonging to q, r belonging to r, and d of q comma r is less than delta, where can they lie? Can we give their anything? Can we say anything about their relative positioning? In terms of the line L.
They cannot be more than delta distance apart from the L.
From L, right? So what Ayush says is that you take delta distance on either side of this line L, and find out this strip of width delta, and if there is some point, so call this region whatever, or yeah. So if there exists such a point, then it has to lie within delta distance from L on either side. Can you see the proof? Both of them have to be there. Okay, so this is wrong. The figure is wrong because this was the last point in Q. No, this is fine. This is the last point in Q. That's right. Yeah. So can you see the proof of this? So what does the lemma say? Let me write it more formally. If there exists Q belonging to Q and R belonging to R, such that d of Q comma R is less than delta, right? Then each of Q and R are within a distance delta from L. Okay, so what is the proof? Anyone? It's not that hard.
If any one of those points were out of more than delta distance apart, then it would automatically make the distance more than delta because the difference in x coordinates would be more than delta.
Exactly. The difference in x coordinate itself will be more than delta because R starts only from here, right? And Q starts on this side. So if there is a point here, then its distance with any point in Q is going to be more than delta because x itself is more than delta. Similarly, if there is a point on this side which is outside the strip, its distance from any point in R is going to be more than delta. Right? So let's just write like this as formally as just two inequalities. So suppose that or let Q and R be such points. Q R be such that whatever Q belongs to Q, R belongs to R, and d of Q comma R is different delta. Then what do we have? X star minus QX is less than or equal to Rx minus QX. Why? Because R is on the right side of X star and less than or equal to, in fact, this should be strictly less. D of QR is most delta. In fact, again, this is also strictly less than delta. So fine. So that means why this inequality? Because this R is to the right of X. So Rx is of course greater than X star. And Rx minus Qx is just the x coordinate difference between Rx and Qx. So the distance is always going to be greater than the at least the difference between x coordinates. And d of Qr by your assumption is at most delta. So the difference between x coordinate of Q and x star is at most delta. Similarly, we write Rx minus x star is less than or equal to Rx minus again Qx is again d of Qr is the same. So this is easy to see. I mean, I have still just written down the formal inequalities to show that why this will be the case. So now we know this, that both Q and R are within distance delta of L. Good. So now we can restrict our search for the combined part. We can restrict our search to this set. In other words, what we have, so let's call this lemma 1. Let's call this lemma 2. And what does lemma 2 say? Lemma 2 says that if there exists, okay, so let this set of points be L. Or sorry, S. Satisfies this B S. So S is a subset of P that satisfies this criteria, right? Okay, good. So what does the lemma say? That if there is, again, Q belongs to Q, R belongs to R, such that D of PQ, QR is less than delta, then PQ belong to S. Right? This is what we show. Or then there exists S comma S prime in S such that D of S comma S prime is at most delta. Again, the same thing. Okay, good. So this set S, how do we get? How do we construct the set S?
We start from the end of the QX array and go left until the x coordinate becomes x star minus delta, and similarly for the Rx.
Yeah, I mean, you can just do it in one pass from PX, that's all. I mean, what you're saying is even more like, this thing that you can go from the middle and to each side. But basically, you can construct it in a linear time. One pass on PX. You go through it, see where, it reaches, and then, you go on either side till the difference is this much. Okay, good. So how to construct the set S? We have constructed. But still the problem is that the set S can be whole of P. I mean, here, who says that these points exist? These points might not exist. Everything can be like within this strip only. So then have we made any progress? So we have, like, quite surprisingly, we have made some progress. And that is like, somehow the beauty of this algorithm is that it doesn't seem like that we should have made progress here, but we have. And that is what the next lemma will say, quite surprisingly. And it might seem magic for now, but let's look at the proof. And so if okay, so let's, before we write the next lemma, we have this set S now, and we also compute Sy is ordering of points in S. According to Y coordinate. And how can we now make Sy? How can we make Sy?
From Py.
Sorry? Yeah, using Py. Correct. So using Py, now you go through this thing of Py and then see whether the x coordinates of them actually lie within the the length delta from the line L or not, and if they do, then you add them to Sy. So again, one pass, order and time. Good. So all this combination thing till now has taken order and time only, right? And that is fine. Now again, we want to use this information to find such points Q and R. And that is where this next, the crux of the whole argument lemma comes, that if there exists S comma S prime belonging to S, such that D of S comma S prime is less than delta, then S and S prime, okay, so let me use small s so that S and S prime lie within 15 steps of each other, or steps meaning positions. In Sy. Okay, so you have this Sy, the sorted array. So what does it say? That you look at 2 points such that their distance is at most delta, then their distance in Sy can be at most 15. So this is what the lemma says. And can someone quickly guess, if we show this lemma, then how can we implement it into the algorithm? I mean, we'll do that formally also, but why are we trying to show this? Why will this be helpful?
You can compare each point with the next 15 points.
Yeah. So now you can do just one pass of the list, as Shravan says, and then you can just go from Sy from left to right, and for every point you can just look at the next 15 points. So for every point you are computing 15 distances, and that is going to be linear still in the size of Sy, which is order n. And if there exists such points such that their distance is at most delta, then you are guaranteed to find them in 15 steps. That's what this lemma says. Cool. So, I mean, I'll come to that again, but let's just, or you can ask later. Let me just prove this lemma. Okay. So, how do we go about proving this? So, let's say divide the region of the plane into boxes of plane which contains the points of a star. S in following way. In like boxes of size delta by 2 times delta by 2. Okay, so this is the length, this is the width, and like 4 horizontal boxes in a line. I mean, 4 boxes lying horizontally in a line at a time. Again, so this is not algorithm, this is just the analysis. Basically, we just want to prove this lemma for which we are doing this. So what do I mean by that? So what I mean by that is we have this line L, right? And then we have this region of delta on each side. And what are we going to do? We just make these boxes. So this is delta. So suppose this is delta by 2. So these square boxes. So you basically tile the whole plane, not the whole plane, the whole region with these kind of boxes, right? But this is again just for analysis. Good. Now, let me just get rid of this thing for now. We'll come to it later.
Excuse me, sir.
Yeah.
Could you repeat how we have tiled the plane?
Could I repeat how we have defined this plane or this region? That's the question. Sir.
Yeah, how we have tiled or divided the plane.
Oh, divided, just like make boxes of delta over 2 times delta over 2 and just start from any arbitrary place and then just tile the whole plane on both the sides.
Yeah, okay, sir.
Okay, so yeah, the starting point or any such thing does not really matter here for the sake of the analysis. Good. So, but the point is that every box has size delta over 2 times delta over 2. So if there exist 2 points, let's say S comma S prime belonging to this S such that S comma S prime are in the same box. So suppose this happens, that there exist 2 points which lie in the same box. Then what is their distance? Can we give an upper bound on their distance?
Delta by root 2.
Less than delta by root 2, right? So good, like you guys are fast in that, because of course the maximum distance can be diagonal. This is delta by 2, this is delta by 2, so you get square root of delta by 2 whole square plus delta by 2 whole square is the maximum distance, which is the diagonal. So you get maximum distance is delta by root 2, which is less than delta, right? So if there exists such 2 points, but the way this thing is formed, these boxes are formed, no 2 boxes are in Q, no box contains points of both Q and R. Right? So what does this mean? That both S and S prime have to be coming from because Q is on this side, R is on this side, Q is on this side, right? But still there is a problem. What is the problem? I'm claiming even this is problematic. Like, you know, this contradicts something.
The minimum distance between 2 points in Q and R was delta.
Exactly. So the minimum distance, delta was the minimum distance between any 2 points within Q or within R. Right? So this is also not possible. So this also leads to a contradiction that SS prime belong to Q. So basically SS prime cannot belong to one, cannot belong to Q, one not and one belong to R. That is not possible. Both belonging to Q is not possible. Both belonging to R is not possible. So what does that mean? What can we conclude from this?
Each box has only maximum 1 point.
So each box has maximum 1 point, at most 1 point. Right? Good. So now suppose, for the sake of contradiction, that there exists SS prime such that they are more than 15 positions apart, and D of S comma S prime is less than delta. Apart in SY, right? So then what will happen? So suppose like, your S comes somewhere, right? So this is your S. But for every let's say 7 points or 8 points, you have to cross one, at least this row. Because each of them can contain at most 1 point, right? Then at most 1 point. So basically the farthest they can be is here and here, if they are to be separated, and then still the distance is 15. At most there are 15 steps, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if it is 16, then they have to be at least 3 rows apart. So there have to be 3 rows of boxes between them. So 16 difference, at least 3 rows of boxes. And what does that mean? That their distance is how much? If there are 3 rows of boxes in between, then what is the distance between them? Can we say something?
3 delta by 2.
3 delta by 2. Which is a contradiction because, again, we had assumed that D of S comma contradiction to the fact that D of S comma S prime is less than delta. And this finishes the proof of the lemma. So this shows that if there exist such points, then we can find them within 15 steps. Right. So as I said, now this is what we are going to exploit now for the algorithm.
Excuse me, sir. Sir, why isn't 11 steps sufficient?
Why isn't 11 steps sufficient? Because you can be here, and so 11 steps, right? So what can happen is that now you have all the points like this. Okay. So 8, 9, 10, 11. Okay, so somehow this point came somewhere here. Actually, we have that y coordinates are different. So actually 11 points might be, 11 steps might be sufficient actually.
So like the distance would become greater than delta at least, greater than equal to delta. So
yeah, so we don't want equal to, we want greater than. So just to and even that I think you can do just by if the y coordinates are not the same, then whatever was the first one, its y coordinate will be slightly lower. So that means there is nothing here. Yeah.
Yeah. Okay.
Yes, I mean, you can optimize it, but again, so even this 15 thing is not very optimized. But what we want for our algorithm is that it's a constant. That's what is important, because then we just go through constant constant steps ahead in the list sy to look for the closest points. Okay. So now this finishes sort of the like the analysis of whatever we were doing, but let's go through the formal algorithm once more. So as I said, so this is the original algorithm which sets up the recursion, and this is the recursive part. So original algorithm first finds this. Okay, so first sorts, as we said, px and py, and then calls recursively. I mean, then calls the recursive algorithm. So this takes time order n log n, right? And then this calls. Now this is the recursive part. In the recursive part, this is the base case. If p is less than 3, then find the closest pair by measuring all the pairwise. So this is order 1 time, whatever, constant time, let's say, times c. Let's find order. Okay. Now these are the recursive calls. So this is order n time in making these lists, and then you just and this we had seen how to construct this in order n time, and then we make the recursive call, 2 of them, which will take time how much? T of n over 2. So 2t of n over 2. Sorry, this one. And this is order n. Now those recursive calls return, and then we just put the minimum distance into the variable delta, order 1 time. You assign x star, order 1 time. You define L, order 1 time. And now S is equal to points in P within distance delta of L. Now, like again, this is just a definition, but again, suppose we want to construct S, then order n time. Now construct Sy, that is again order n. Okay. Then for each point S in Sy, compute the distance from S to each of the 15 points in Sy. Right? And this is again order 1 time, which is like 15 times some constant time, which is again constant. And then you find the minimum. So this one, the whole thing takes order n time. This whole thing takes order 1 time. Okay. Okay. And then you just see what is the situation that, okay, if this is smallest one is less than delta, then you return that. Else you return whatever Q or R, whichever was smaller. So this also can be, this is just comparison. This can be done in order 1 time. So that is it. This was also order 1. This was order n log n. Right. So let's do the runtime analysis. So T of n is order n log n, which is the setting up time plus T of this procedure. Let's say that is T prime of n for recursive. And what is T prime of n? T prime of n is 2Tn over 2 plus order n. So T prime of n solves to order n log n, and put that here, you get T of n is also order n log n. Okay. So this is not that hard to do, and just quickly, like, again, a formally proof of correctness. So proof of correctness will be by induction on size of P. So if P less than or equal to 3, base case handled by order one time. Okay, correctness we have to do. So base case anyway handled explicitly. Okay. Now suppose you have some P, and then you constructed, if P is greater than or equal to 4, then from P you constructed Q and R. Both of them are smaller. So you can apply induction hypothesis. So there are three cases. The smallest pair S prime belong to Q. So let SS prime are the smallest pair. Then by induction hypothesis, you can say that the algorithm returns correctly because the algorithm calls the algorithm itself on Q. Again, if SS prime belongs to R, then again induction hypothesis. And if S belongs to Q and S prime belongs to R, then due to lemmas whatever 1, 2, and 3, you are sure that you will find the correct pair. Again, like, you can write a couple of more lines that, okay, this distance, since it is smaller, then, like, it will be found out. They have to be from this lemma within the distance of delta from the line L, and then that will be found correctly by, within the set S by lemma 3. So any questions about the algorithm or about the analysis or the correctness? Any questions? Please ask. Okay, so I mean, so again, just another point that I forgot. So why was I saying that, or why did we go through the one-dimensional thing and try to say that we want to do something similar? Because again, we wanted to do one pass just like we did in one dimension, and then we wanted to do something similar that, okay, we do one pass and somehow find the points there. But of course, that cannot be done in like by itself. But if we have more information because of the recursion, so the recursive calls gave us more information regarding delta. That, okay, what is the closest distance on this side? What is the closest distance on that side? And then we constructed this set S in a particular way, and using that, we were able to exploit and find the closest. Okay. So no questions, I guess. Okay, cool. So if there are no questions, then let's meet on Tuesday. Thank you for coming.